in this session, we have a parallel lightning talk. So we have about 4 talks and then a break and then another 4 talks. The rules are like it was yesterday, namely each talk is exactly 10 minutes and I will announce when there are 2 minutes left and 1 minute left. So I think we can just start. Just a second. So Danil, you're the first speaker, right? So
right.
So I'll put the spotlight on you, and maybe you can start whenever you feel ready.
Okay. Hello everyone. Our talk is called on uniform Hilbert Schmidt stability of groups. It is presented by Danil, Akhtyamoff and Alon Dogon. Our advisor is Raz Slutsky, and we are master's students at the Hilbert University of Jerusalem. In his book, Stanislav Ulon proposed the following question, which we will first state informally. The question asks the following: given a map between groups that is close to being a homomorphism, can it be approximated by a genuine homomorphism? Okay. Let's now proceed to formulating the question more rigorously. Let's first give the following definition. Given a group G, a metric group H with metric D and a positive epsilon, and the map phi from G to H, which is not necessarily a homomorphism, it is said to be an epsilon homomorphism if for all G and H from G, the distance between phi G and phi H and phi GH is less than epsilon. And now, given a group gamma together with a class of metric groups, we say that gamma is uniformly stable with respect to this class. If for any positive delta there exists a positive epsilon, such that for any h from the class and for any epsilon homomorphism phi from gamma to h, there is a genuine homomorphism pi which approximates phi up to delta. So I'll give you a few seconds now if you want to read the definitions again. Okay, I hope you're fine with the definitions now. No, this question has been studied by some researchers. In particular, there is a following quite famous result due to Kashdan in this area, which says that any amenable group gamma is uniformly stable with respect to the family of all unitary groups endowed with the operator norm. For those who don't know about amenable groups very well, I will just say that it's a quite big class of groups, which, for example, contains all finite groups and all nilpotent groups. But on the other hand, it does not contain the free group, for example. Now, this question has been further investigated by Burger, Azal, and Tom. And in the paper, they first of all they proved that if gamma contains a non-abelian free group, then it is not uniformly stable with respect to the class of all unitary groups with the operator norm. On the other hand, they prove that if one takes SLNO, where n is greater or equal 3 and O the ring of integers of a number field, which by the way contains free group, a non-abelian free group, then it is uniformly stable with respect to a smaller class. That is, we restrict ourselves from from all unitary groups of all Hilbert spaces to unitary groups on finite dimensional Hilbert spaces, and again endowed with the operator norm. And by the way, it is still unknown whether there exists a non-abelian group which is uniformly stable with respect to the class of all unitary groups of all Hilbert spaces. But the first theorem kind of hints that even if it exists, the examples should be very hard to build. No, thanks. I'm now giving the word to Alon.
Thank you, Danil. Start sharing my screen. Can you please stop sharing yours? Otherwise, thank you. Okay, great. So again, thank you, Danil, and I'll continue from where you stopped. So now we get to our result. And in all the history Danil mentioned, it was studied, this stability property was studied with respect to the operator norm on either infinite dimensional spaces or on finite dimensional ones. But here we want to study another very important matricial norm, which is defined, which we consider on UN, which are just the unitary groups of finite dimensional Hilbert spaces, and it's defined as follows. The norm of a matrix A is basically, here's the formula is written, but it's basically just treating A as an n times n dimensional vector and looking at its usual Euclidean norm, but normalized by square root of n. Great. So this is a very natural norm, but it has very different properties compared to the operator norm on unitary groups. And again, these questions of stability, we consider all finite dimensional unitary groups. So if we ask whether a group is stable with respect to the Hilbert Schmidt norm, it might be a different question compared to asking whether it's stable to the stable with respect to the operator norm on UNs. Of course, okay, given the norm, we define the metric, which enables us to talk about UN as a metric group, and thus the definition of stability can be considered. And our result really asks what groups are stable with respect to the Hilbert Schmidt norms on all UNs. And somehow the situation here is quite different compared to the operator norm, which Kashdan showed all amenable groups are stable. So what our result says that under the assumptions of finite generation and residual finiteness, which are quite mild, a group will be stable in the Hilbert Schmidt sense if and only if it is virtually abelian. So the virtually abelian groups are amenable, but they very much are, the class of amenable groups is much larger. So they are under these assumptions, there are much less Hilbert Schmidt stable groups. So in the remaining time, I'll try to sketch how we prove this theorem, and there are two directions. Let's start with one of them. So the only if part, we want to show that if a group is Hilbert Schmidt stable, then it is virtually abelian. Under the assumptions I mentioned. So the first logical implication is that assuming Hilbert Schmidt stability, we can prove that this is actually an observation that was made for specific cases in the past by Becker-Lubotsky, by Burger-Ozawa, Tom, and Gauss-Hatami in different forms. But basically what happens is that this property of stability implies that dimensions of irreducible finite dimensional representations of gamma, of course, we're all talking about unitary representations, they have there is a bound on their dimensions that only depends on gamma. And then under the assumption, so this is a representation theoretic property, and then under the assumption of finite generation and residual finiteness, we can show that gamma is virtually abelian. Okay, this is one direction, and it is not so long, but it's still non-trivial. But the other direction requires much more heavy work. Specifically, okay, what do we want to prove here? We want to prove that if gamma is virtually abelian, then it is uniformly Hilbert Schmidt stable. And here we do not need to assumptions of a residual finiteness or finite generation. So the first observation is very simple. It's gamma is amenable. But the second implication here, this was some very, I think, groundbreaking work made by Marcus de Chiffre, Naotaka Ozawa, and Andreas Thom very recently, where they showed that amenable groups are not Hilbert Schmidt stable, but they possess a slightly weaker property called flexible Hilbert Schmidt stability. And this requires quite a lot of work. And what we did is basically show that when gamma is virtually abelian, it can be shown that gamma is, this weaker property actually implies the stronger property of stability. But that's about it, and I thank you for listening to us.
Thank you very much. It was very interesting. Okay, so we now move to the next talk. Tamar, are you here?
Yeah. Hi.
Oh, I see you. Perfect.
Okay.
You can start whenever you want. Good luck.
Okay. Thank you. Okay, so thank you for this opportunity. I'm going to talk about profinite completion of three profinite groups. So I will start with some definitions. If G is an abstract group, which means without any topology on it, the profinite completion of G is a pair of a profinite group, which we denote by G hat, and we need to justify it, but it will come in 1 second. And then homomorphism from G to G hat, which satisfy the following universal property. Any homomorphism from G to a profinite group H can be lifted in a unique way to a continuous homomorphism from G hat to H. So it is easy to see that if the profinite completion of G exists, then it is unique. And so we can call it G hat. And it is actually exists for every abstract group G. We have an explicit construction. G hat is the inverse limit of all the finite quotients of G, G modulo H, where H is normal subgroup of finite index. And it makes a directed system in the natural way. If G is a profinite group, it is also an abstract group, so it has a profinite completion itself. Naturally, we would like to think that G hat will be equal to G, but it's not necessarily true, because G is known to be the inverse limit of all the quotients of the form G mod U, where U runs over the set of open normal subgroups of G, while G hat is the inverse limit of G mod U when we run over the set of normal subgroups of finite index. Now, every open subgroup has finite index. It is known in every compact group, but there might be subgroups of finite index which are not open. So G is not necessarily equal to G hat. We say that G is strongly complete if G equals to G hat. So G is strongly complete if and only if every subgroup of finite index is open. Okay, for example, if we take the product of Z mod 2Z over an infinite set I, then it is known that the number of open subgroups is the cardinality of I, but this is actually a vector space over Z modulo 2Z of dimension 2 power the cardinality of I. So the number of maps, which mean homomorphisms to Z mod 2Z, is 2 power the cardinality of I, because we only need to determine on the basis where we send every element. So we just need to pick a subset and send on this element to 0 and the other to 1. So this is the cardinality of the power set of 2 power the cardinality of I. So it has much more subgroups of finite index than open subgroups. So this is the classical example for a finite group, which is not strongly complete. Okay. Moving to free profinite groups. Let X be a profinite space. A free profinite group over X is a profinite group. We denote it Fx, and then the continuous function from X to Fx, such that every continuous function from X to a profinite group H can be lifted in a unique way, obviously, to a continuous homomorphism from Fx to H. So again, for every profinite space X, the free profinite group over X exists, and it is unique. Okay, we don't want to talk about profinite spaces, but about pointed profinite spaces. So first, we need to notice that every profinite group is also a pointed space. We can take E to be the distinguished point. And now we talk only about pointed maps, obviously. So we want to generalize the concept of free profinite group over an abstract set. When we take X to be a finite set, it's not a problem because obviously we can take it as a discrete set and it is profinite. So this is a profinite space and we have no problem. But if X is infinite and we want to consider all the possible maps from X, we must think of X as a discrete space, and then it is not profinite. So we can sort of make it into a profinite space by taking the one-point compactification. And the one-point compactification of an infinite discrete space is a profinite space. And it is also a pointed space by taking asteroids to be the distinguished point. So if X is an infinite set of cardinality M, the free profinite group over the one-point compactification of X is called the free profinite group over the set X converging to 1, because continuous map from the one-point compactification corresponding to converging to 1 maps from X. And we denote it by Fm, which means that the cardinality of X is the only thing that really matters. X is a basis for Fm, and M is called the rank of Fm, obviously. So Fm is not strongly complete, which means that it has a profinite completion, which is a new profinite group. And it's natural to ask, if we take a free profinite group and we complete it, do we get a free profinite group too? So the first observation we need to make is that if Fm at would be a free group, then its rank must be equal to 2 power 2 power n. We don't know that this is a free group, but if it is a free group, then it will be F of 2 power 2 power n. So what tools do we have to determine whether a profinite group is free? The main tool is embedding problems. Embedding problem is a diagram where phi is is a continuous map because we talk about profinite groups, and it's an epimorphism. And a solution to the embedding problem is an epimorphism from G to B, which makes the diagram commutative. Now, let G be a profinite group with omega 0 G equals to M. It means that the number of open subgroups is M. Then G is free of rank M if and only if every embedding problem of finite groups, which means that B is finite, has M different solutions, which is the maximum number of solutions that G can possess, because the number of open subgroups, it's actually the number of epimorphisms to continuous epimorphism to finite groups. Okay, and we don't need to look about all the problem. Yeah, okay, I will make it short. It's enough to take A to B minimal normal. So our partial results is that to determine if Fm at is free profinite group of rank 2 power 2 power m, because this is the only thing that can happen, is equivalent to determine if every abstract embedded problem, which means that phi may not be continuous, it can be continuous, but not necessarily, has 2 power m abstract solutions. And what we managed to prove is that in the case that phi is continuous, then there will always be 2 power m abstract solutions. So it is known that there are m continuous solutions, but apparently there are extra 2 power m abstract solutions. Okay, this is not even half the way because there are many maps which are not continuous, but that's what we did. Thank you.
Thank you so much. Great.
I stopped it.
There is some feedback. Okay. So we move to the next talk. I remind everyone that it's part of the rules of the session that I interrupt and say 2 minutes and 1 minute. It's not to stress you out, but it's part of the game. The next talk is by Tamar. So Tamar asked not. So I start the recording again. The next talk is by Gal Dor.
Hello, everyone.
Hi, Gal. You can start whenever you want.
Okay, so let's begin. So my name is Gal, and today I'm going to try to show you a nice little trick that I came up with, that I basically encountered during my research. Now, some tricks are like this very, formulaic things. You do this, you do that, and then you get an answer. This one is something that you need to tailor to your situation. It's not as mature as other tricks, but hopefully it will be something that other people can also use and find interesting at the very least. So what's the setting? What kind of object is this little idea about? So consider some group. Maybe it's a finite group, maybe it's a p-adic group, maybe it's an adelic group, depending on what you're studying. And you are naturally interested in its representation theory. Now, one important tool for studying the representation theory, even if you only care about irreducible representation, is the category of the representations of G modules. That's something that a lot of people do. It's very natural to look at it. Again, even if you only really care about the irreducible representations. Now, a different kind of question that often comes up is, okay, I have a specific G space, like some space that G acts on, and I have some space of functions on it. If it's a finite group, then maybe it's just all functions. Maybe it's the set of smooth functions if I'm in the right setting, etc. And I want to understand which representations of G appear in functions on X. Now this, to be a representation that appears in functions on X, that's a property of irreducible representations. It doesn't really make sense for arbitrary representations. However, the trick, the idea is that sometimes you can build a category that looks kind of like the original category of all G modules. It's abelian, you can take quotients, you can take direct sums, etc. But its irreducible objects, the ingredients it's composed of, are only the ones that appear inside functions of X. Now, sometimes you can do this artificially, but it's very useful to have some kind of nice canonical construction of this kind of category, because that way it lets you actually say interesting things about those irreducible representations. So what's the basic idea? First of all, of course, we want to build a category, and as you all know, all categories are model categories, or at the very least, that's the only reason, that's the naive way to construct a category. So we want to construct some model category that's related to functions on X. So a naive idea would be, which is one that doesn't really work, to just say, okay, let's create some kind of ring structure. Let's make functions on X into a ring, define a multiplication operation, and consider the category of functions of modules over this ring. Now, this doesn't really do what we want because multiplying this tensor product of G modules doesn't really have anything to do with their decomposition. So let's just give an example to show what I mean. Consider GL2FP, and that it acts in the canonical way on a two-dimensional vector space. Then if you take this two-dimensional vector space, which is an irreducible representation, and you tensor it with itself, then it decomposes into two completely different irreducibles, one which is three-dimensional, the other is one-dimensional, and they have nothing to do with the original one. So there's no really any reason to expect that the modules of this ring functions on X, which however way you gave it a ring structure, there's not we haven't really decided yet. There's no really any reasonable way to expect that the irreducible objects of this category will have anything to do with the irreducibles that appear inside functions of X. Okay, that's a problem. And now here's the main trick, the idea that that I wanted to share, that I was so excited by that I wanted to share with you guys, which is that you can come up with your own tensor product. That is, there is a notion that is called a symmetric monoidal structure. What does it mean? It means that you construct for any pair of G modules a new one, which you call their product. It has to satisfy some bare minimum of property, and it has to satisfy some bare minimum of properties and some maybe extra structure, so that it will make sense to talk about rings with respect to this structure and modules with respect to this structure. Basically, that's the categorically minimal thing that you need in order to talk about rings and modules and do all of the, and basically algebra inside your category. So the thing is just that if the usual tensor product doesn't suit your needs, maybe you can come up with your own one. So let me give an example. Suppose that you have an abelian group, then there is something called the relative tensor product. That is, if I have two representations of G, then I can consider the tensor product as a vector space, but quotient it out by allowing G to move across the tensor product sign. So I can have like a GA times B, the same as A times GB. And because G is abelian, then the result is also a G module. So this is a relative tensor product, called the relative tensor product. Everyone is, most people I expect have seen it in some basic algebra course. And this is, so this is a very natural notion, but unlike the usual, the previous tensor product, this one respects the spectral decomposition. So if I tensor someone with a representation, then I will only ever see representations that appear inside one of the side of the tensors here. And now, because we changed what it means to be a ring with this, by introducing this different kind of symmetric monoidal structure, it turns out that what it means to be a ring with respect to this one is that it means to have a convolution product. And indeed, many spaces of functions over abelian groups have convolution products. So in other words, they have canonical ring structures with respect to this different symmetric monoidal structure. And then you can study the modules and everything with it. Now, that's something that people have been doing forever. Yes, I didn't come up with the idea of, okay, introduce a convolution product and study the module, or just study, use that extra ring structure to understand your space. But the thing is that you can do this even if your group is not abelian. So the example I ended up coming into with my research was GL2. And it turns out that for all kinds of different G spaces, for example, you take GL2 modulo the diagonal subgroup, or you take in the adelic case, for those of you who know what this means, you take the adelic quotient, then it turns out that you can define a different symmetric monoidal structure on the category of GL2 modules. And this symmetric monoidal structure respects the spectral decomposition. So the irreducible representations that appear in your new category will be the right ones. And many spaces have natural and canonical ring structures with respect to this. Some kind of non-abelian convolution products, even in this kind of quotient spaces. Now the methods that I used specifically were I tailored some product that works for GL2. I believe that it might be possible for GLN as well, and it might be more complicated for different groups. But the idea is basically that just it needs to be tailored to the specific situation. So what did I tell you? What's the bottom line? The bottom line is that it's much easier to study modules and algebras than it is to study just bare spaces. So you really want the objects that you're studying to be modules and algebras and to have products, etc. Now, unfortunately, sometimes the very notion of multiplication is not useful to you. So if the notion of multiplication is not useful to you, you can make a new one up, and that turns out to work and give nice results in important fields of mathematics, or I hope they're important. Otherwise, I'm wasting my time studying them. So that's it, basically. That's the point I wanted to tell you. And if you want to read more, then you can read my thesis, hopefully to be published soon. And that's basically it. That's what I wanted to say.
We have 1 minute and a half for questions since Gal finished early. So if someone wants to ask a question, a quick question, we have time. Yeah, I think that people didn't prepare to ask questions since that is not a... So
no, I can ask a question. I can ask a question. Why do you call them distinguished then?
So usually it's just an irreducible representation, which has a vector that's invariant with respect to some subgroup, is called distinguished with respect to this subgroup. So in the special case, when the space you're studying is G mod H, then the irreducible objects of the category that you're hoping to build are called distinguished irreducible representations. They are distinguished with respect to H.
Okay, so does your new structure give you some insight into distinguished representations? I mean, these have been studied.
Yeah. So probably this is not a good stage, a good forum to talk to give you a lot of details, but I hope so. That's basically my thesis. Yes, I gave some specific.
So I have to read.
Or we can talk later, but yes.
Okay, great. Actually, you can talk now because we have a long break until 12 or 17 minutes break. And then we resume at 12, okay? So I suggest that you talk now or not, as you wish. So at 12 o'clock, we will have the next talk by Etai Leumi. So see you soon.
I think I'm at 12.
Yeah, I was just gonna say that. I think Elyasheev.
Sorry, by Shivi. I'm sorry. My mistake. My list, I skipped. I thought you were before the break. I don't know. Anyway, the first talk after 12 is by Shivi and then by Etai, not as I said. Thanks for correcting me.
Okay, so I can get back to my question. I haven't looked. I looked at your work related to the Dixmuir-Malyavin lemma, and I thought that was your thesis. That was part of.
It's part of my thesis. Just at some point during my thesis, I ended up trying to work with not with function fields, but with Adels over number fields and things like that. And so I ended up needing some good notion of topological vector spaces, and I tried to make do with standard tools, and it didn't really fit. So I ended up needing to use Bornological vector spaces. They had much better categorical properties, and since I was doing categorical stuff, it suited me much better. And I just and that was and what you saw was basically a the technical introduction to using that tool that I used in my thesis. So, because I needed Bornological vector spaces, then I wrote down some work that was related to what I was doing.
I see. Well, yeah, that was already very useful, but I don't know. Distinguished representations have been studied for such a long time by so many authors.
So the focus is not, I'm not trying to study distinguished representations in general.
Okay.
Specifically, I was looking at automorphic representation theory. And the main useful case that I was able to construct is that I actually ended up with a category of abstractly automorphic representations. That's the case of being distinguished for the lattice of rational points. And that was the main case I cared about, and over there, that's where most of my results are.
I see. And you're staying this year. You're still in Israel, right?
Yes.
Obviously, no one can move. We're thinking about inviting you to our seminar in Bar-Ilan, where we can really give you the first degree cross-examination.
Not examination. We want to see. We want to hear the entire talk, not just 10 minutes.
I don't know if we want to hear or we want to ask and cause problems.
I wanted to ask if it's easy to state it in a Lie algebra version. What you're saying.
I have not tried to look at any kind of Lie algebras. I would be very interested to see, even just, most of my tools are specialized at this moment to GL2, but I haven't tried looking at a Lie algebra version for even for GL2. So that might be a good direction for future research.
I personally have classes of modules for superalgebras which are not close to tensor products. And we really like, I mean, it sounds like a nice thing to
So specifically for GL2, I have a tensor product. One of the big technical tools is a different kind of tensor product for GL2 that tends to respect a lot of classes of representations. So I think maybe this is something that would be useful if that's what you're looking for. So I can maybe say a few words about that if you want, but.
So yes, I'd like to ask. Can I interrupt you, Shifi, with your line of?
Sorry, I'll mute myself.
Okay, so what happens when you have? You are probably familiar with the tensor product for the components of a Levy subgroup. You just think about periodic groups.
Yes.
Okay?
Yes. Mm-hmm. So if you have a component, then what happens is that there's this parabolic induction functor from the representations of the component. Now for GL2 specifically, the components that you care about are GL1 times GL1. And in that case, well, GL1 times GL1 has an obvious relative monoidal the relative tensor product makes sense there, and that's probably what you want to look at. And it turns out that the functor of parabolic induction from GL1 times GL1 to GL2 with the exotic symmetric monoidal structure, this functor is non-unital right lax. So so I'm not sure if that's maybe so right lax means that you have a map from f of a times f of b to f of a times b. So it sends rings to rings essentially. Non-unital means that it doesn't necessarily send the unit of the ring to unital rings to unital rings. But also it's very close to being just completely right lax, to being unital. Just you need to invert a specific morphism before that happens. But the bottom line is that it approximately sends algebras to algebras. And you can do a lot of stuff with that. I have that's outside the scope of my thesis, but I wrote there's a separate paper about that I'm writing right now. And basically what you can do is that you can use this to make sense of a lot of stuff that appears naturally in the theory of automorphic representations. You can basically reinterpret some statements about Eisenstein series and the functional equation for Eisenstein series, or just even the local intertwining operator, stuff like that, makes a lot of sense when it's formulated in this language. They all become statements about dualities of certain multiplicative structures. Okay, well, I'm interested in slightly more
I would say esoteric, but now becoming a common situation. I will ask you, I don't want to burden you too much with the further questions. Maybe we'll invite you to give a talk once the semester starts, and
Sure.
you'll have to be prepared for more.
For a deeper interrogation.
Before or after?
Sure.
Oh, spotlight.
שיבי, של מי אתה סטודנט?
של אורי בדר בוויצמן.
אורי בדר. חשבתי שאורי בדר הוא ממשרד החינוך, ככה היה כתוב באיזשהו... הוא כאילו גם כאילו עושה התנדבות במשרד החינוך, לרשות מקצוע?
אני חושב, אני רואה שהוא בפרטיסיפנס.
מה?
אני רואה שהוא
הוא פה, אורי. יפה. ואיפה עשית תואר ראשון?
באוניברסיטה העברית.
יפה.
כן, הוא מנחה מצוין, ממש.
הוא אמר שהוא לא מקשיב.
אז...
נראה לי שהוא רצה לקבל את המחמאות. זה טוב, תמיד טוב לתת קרדיט.
אני לא רוצה להתחיל מוקדם, שלא יחשבו שאני כמו סר.
זה היה דבר מאוד מאוד מוזר. הוא התחיל 5 דקות לפני הזמן, והיה ברור שכאילו המשיכו נחיל של אנשים להיכנס תוך כדי. האנשים ישבו על השולחנות, מאוד, כאילו הופעת רוק. באמת הייתה הרצאה טובה, אבל...
אפשר להסתופר? טוב, אני אשתף את המסך, נראה שזה...
אתה יכול לקרוא. נתחיל עוד 5 דקות, אבל...
כן. רואים את המצגת?
כן, רואים מצוין.
אוקיי, בסדר. זה מה שחשוב.
היי, שלום לכולכם, מקווה שנהנתם בהפסקה. שאלו אותי איפה התפרסמו הסרטונים של ההרצאות, אנחנו נעבוד על זה ברגע שהכנס ייגמר ונפרסם את כל הפרטים באתר של ה-IMU. אז עוד זמן קצר, לא יודע להגיד בדיוק כמה, כל הפרטים יהיו שם. אני שמח, בהרצאות לפני ההפסקה שכחתי לציין את המוסדות של התלמידים, אז, sorry, I'll switch to English, my mistake. So before I forgot to say the institute of the speakers before the break. So the first talk by Danil and Alon, Danil and Alon are from the Hebrew University. Tamar Bar-On is from Bar-Ilan University. Bauer is also from Bar-Ilan University. Gal Dor from Tel Aviv University. And now we are approaching the first talk after the break by Elyasheev Leibtag. Did I say it correctly?
Yeah, Leibtag.
Leibtag. It depends if you read it in German or in English.
In English or in Hebrew also, like Leibtag.
But in German, it's Leibtag, I would say. I spent there a year and a half.
Yeah, I actually don't think their origins, probably not German, but.
Anyway, so Elyasheev Leibtag, and coming from Weizmann Institute, and please, Shivi, start at your convenience.
Okay, thank you for having me. I want to talk today about topological groups, which we all like and know, and actually talk about a certain property of these topological groups and show how algebraic groups behave well with respect to this property. So let's begin. Again, this is a work from my master's, done advised by Uri Bader in Weizmann. So let's define the property we're talking about. So let G be a topological group. We say that G is sealed if any continuous homomorphism phi into any topological group H, the image phi of G is a closed subgroup of H. Okay, so it's a property of the group G, having that any image of the group under any homomorphism, so any way it embeds into another group, the image is closed, and just so we're all on the same page, all our topological groups here will be Hausdorff. Okay, and right, we want all our spaces in general to be Hausdorff, so it's also a good idea to want our images to be closed, right? We want the co-kernel to be a Hausdorff space. So let's start with a non-example, just showing how it's not a very easy property. So a nice topological group like the additive group R is not sealed. And how we can say it is, well, we just look at the irrational winding on the torus. Okay, so we just take some irrational number and we take the slope on the torus and we wind around it like in the picture. And we can see that, well, the image is dense in the torus, but it's not onto, right? Rational points can't be attained. So the group R is not sealed. It has a dense, not closed image, right? The image can't be closed. This is not very specific, actually. In fact, any abelian group, if it's sealed, it's compact, right? And R is not compact. So, so this is not the case. This can be seen maybe using stuff from Tamar's talk on the profinite completions and Bauer compactifications. So examples, who is sealed? Okay, well, abelian groups, if they're not compact, are not. But okay, compact groups are sealed, right? The image of a compact group is compacted. All spaces are Hausdorff, so this is closed. And next example was actually shown by Goto and Omori in the 60s. They showed that semi-simple Lie groups with finite center are sealed. So any homomorphism from SLN R into any other group, the image will be closed. Also, about just a few years later, was shown by Uri Bader and Tzachi Gelander that semi-simple algebraic groups over local fields, saying we switch this R into some p-adic field or any local field, actually, even with positive characteristic, then the image, again, under any homomorphism of this group is closed. So these are similar examples of sealed groups. And besides that, there aren't so many examples. It wasn't studied too much. It's very related to minimal topologies in groups, which was studied, and we can talk about it later. So the objective of the work is just, let's try and provide some more examples of sealed groups, like the ones above, and maybe give a criterion for a group to be sealed. What can we say about a group in order to make it sealed? So in order to find the criterion, let's look at basic properties of sealed groups. So let G be a sealed group. It's evident that the center of G is sealed, and the center is a abelian group, so the center of sealed groups must be compact. And it's also evident that any normal subgroup of N, G mod N, will be sealed, right? Because you just concatenate the map from G to G mod N. It has the same image, it should be closed. So these are two very basic, very necessary properties for sealed groups to have. And actually it was shown by Mayer that taking a connected group G, then the following is equivalent. G is sealed, and for any closed normal subgroup, the center of the quotient group is compact. So he showed that in the case G is connected, these very mild assumptions, right? These necessary assumptions on the group to be sealed are actually enough. So if the center of the group of any quotient group is compact, the group itself will be sealed, assuming G is connected. He uses connectedness because he goes through a Montgomery-Tsipin result, maybe kind of reducing it to the case of an algebraic group. So here we can ask a question: can we give the same criterion for non-connected groups? Well, no, we cannot. And a nice example I like to think about is, so let's look at the group SL3Z. So binomial subgroup theorem of Margolis, it has only finite quotients. So of course it has that the center of any quotient group is compact, but it's not sealed. It embeds densely into the p-adic integers, right? SL3 over the p-adic integers. So what can we say for non-connected cases? So the attempt is to maybe try and understand conceptually, or give my own concept of why SL and QP was actually sealed, and try to include this way more groups and maybe give a criterion for this family of groups. So the theorem from the master's thesis was as following: let K be a local field, like QP as before, and G will be an irreducible split. This assumption may be omitted, maybe working it now, algebraic K group, and look at G to be just the points over the local field. Okay, so think of your matrix group with points over a field, and the following is equivalent: G is sealed, and for any normal subgroup N, the center of the quotient is compact. Okay, we get the same criterion, not assuming connectedness, but assuming irreducibility of algebraic. So we get a whole new family of sealed groups. For example, the group SL2QP, semi-direct product with QP squared, when the action is just by action of a matrix. And this is a new example of a sealed group. So I want to go quick outline of the proof and how we've done it. So the main observation was as following: if we take a local field K and we look at the action of the multiplicative group K star on K, and it can act actually in many ways, and we look at some action with some power. So we obtain a semi-direct product, a group G, K star times K. Okay, and in this case, we have a lemma saying that for any group H and any continuous homomorphism phi from G to H, so of course G is not sealed, right? Because it has a non-compact quotient, but the subgroup phi of K, right? This little normal subgroup will be closed in H. Okay, and the way we showed it is that the image of K is actually the K star product, and it gives it a K model structure. And the topological K model structure is actually closed in any topological space it lives. So just to outline as a proof, now G will be the group that we started with, algebraic group, right? And so let's just assume G has trivial center because the center is compact. It's okay. And what we used is we used the Levy decomposition of G, where L will be semi-simple since it's compact center, and U will be unipotent. This unipotent group is nilpotent. So what we want to show is that phi of U is a closed subgroup. Okay, and we do this by induction on the nilpotence degree of U. The base case showing that phi of U, phi of U is closed is, okay, U is abelian nilpotent subgroup, so it's actually isomorphic to k to the power of n, and the action of L on U is some rational representation of this semi-simple group. What we can do is we take a maximal torus in L and we decompose U into root spaces. Okay, each root space is kind of similar to the situation where we had above, where K star acts on K. And in this case, we can show that each root space, actually its image is closed. Somehow we are able to glue all these root spaces together inside the image and show that the image of U is itself a topological K module, a finite dimension, and therefore it's closed. So what we have is we have phi U is closed, phi L is closed, and since L is semi-simple by the Gilander-Bade result, and we get that the semi-direct product will be closed as well. Thank you.
Thank you very much.
I will stop sharing somehow if I figure it out.
Just a second. Ty, where you are?
Hello.
Yeah, I see you. Okay.
What's up?
So the next speaker is Etai from Tel Aviv University. Etai, you can start whenever you're ready. You ready?
Thank you. Hey, everyone. So I'm here to talk to you about the LCM problem for function fields. This is also a part of my master's degree, and it's under the supervision of Professor Zev Rudnick, to whom naturally I owe a great deal of this. So let's begin. So first, when talking about an LCM problem, we'll start with something we all know, which is the definition of the LCM. So given a sequence of integers, the least common multiple, L, is uniquely defined up to sign by requiring first that L is a common multiple, and secondly, which is the minimality criterion, that if some other integer L prime is a common multiple of the sequence, then L divides L prime. Now in 1850, Chebyshev showed that these two statements are equivalent. The right-hand side being the prime number theorem, where pi n is the prime counting function up to an integer x or a real number x, and the left-hand side being an asymptotic estimate of the log of the LCM of the first n integers. So essentially what Chebyshev's idea was that this guy right here is itself some sort of a prime counting function. And when the prime number theorem was proved, essentially what was done was proving the left-hand side and deriving the prime number theorem from it. And so after this idea became so fruitful, it was generalized to the study of least common multiples of polynomial sequences. The first case being the linear one, which was also solved. So if we let f be some linear polynomial with integer coefficients, then the log LCM of fk, when k goes to the numbers 1 to n, is asymptotically equivalent to some constant depending on f times n as n grows to infinity. So here the linear case has linear growth in n. And this itself is also a consequence of the prime number theorem for arithmetic progressions. Now in 2011, Silorello conjectured that if we let f to be an irreducible polynomial with integer coefficients of degree d, which is at least 2, then the log LCM of fk, when k goes to the integers 1 through n, is asymptotically equivalent to d minus 1 times n log n as n grows to infinity. So now we have a faster growth rate than a linear one. And Silurello proved this estimate for quadratic polynomials, but if degf is d strictly greater than 2, the conjecture is still open. And even though a good upper bound is known and a lower bound of the correct magnitude, even a single example is yet to be proved for the case d being strictly greater than 2. So for instance, for the polynomial x to the power 3 plus 2, we do not know this estimate. And I'll just say one more thing, that the linear case had a very strong correlation to prime counting functions. And now when the growth is not linear, this correlation is somewhat obscured. And in our work, we study the analogous LCM problem, but for function fields, as function fields allow us a bit more leeway and a bit more tools to handle this problem. So now I'll start to describe the function field analog. So when we're talking about function fields, my ring of integers is essentially this right here, this ring right here, fq of t. So this is polynomials with coefficients in some finite field. And we let f be a polynomial over the variable x with coefficients in this ring. And we take the degree of f to be d over the variable x, which is at least 2. And we further assume that f is monic, separable, meaning no multiple roots, and absolutely irreducible. If you do not know what absolutely irreducible means, just think of irreducible polynomials. It's not too restrictive, this assumption. And now we set LF of n, this is our LCM sequence, to be the LCM of fq when q goes through the entire set of polynomials which are monic and of degree precisely n. And so keep in mind that LFN itself is a polynomial in fqt. So the analog of Silurello's conjecture for function fields is that the degree of LFN is asymptotically equivalent to d minus 1 times q to the n times n. And here the degree is the analog of the logarithm. It's a function that takes multiplication of degrees to an addition. And here q to the n is exactly the size of this set right here. Q to the n is the size of the number of polynomials which are monic and of degree precisely n. And n is like the analog of log of n, of log of q to the n. Now, first we did some basic results. These results are just translations of known facts from the integer case to the language of function fields. So we took what is known, took the proofs, and for every tool we have an analog tool in function fields, and that's basically how we show this stuff. So these results are in some way just a verification that we got the setup right. So firstly, we have an upper bound, which is deg LF of n is asymptotically less than d minus 1 times q to the n times n, which is a good upper bound. And it's the correct magnitude and a precise constant. Secondly, we showed a lower bound, which is deg LFN is greater asymptotically than d minus 1 over d squared times q to the n times n. And here we have the correct order of magnitude, but not a precise constant. And thirdly, we showed the quadratic case in the same fashion as Silurello did. So if d is 2, the degree is 2, then deg LF of n is q to the n times n plus some, excuse me, some error term of magnitude q to the n. And now to show our main result, we have the following theorem, which states that for the following set of polynomials, we know Silurello's conjecture. The first part being x to the d plus ht when q is congruent to 1 mod d. Second part being x to the p to the k minus ht to the p to the k minus 1 times x plus ht when q is p to the m. So q is a prime power p, and this is also, the degree is also a prime power of the same p. So the characteristics divides the degree here. And k must divide m for our methods to work. This k right here divides this m for some integers, some natural numbers k and m. And this is for any ht which is separable and of degree at least 1. So for example, you can just take ht to be t. So here finally in the function field case, we have some set of polynomials with arbitrary degree. This isn't the entire conjecture, but this is a bit of exciting. And the defining property of the set is that the double polynomial, fx minus fy, factors into a product of linear terms. So for instance, if we take fx to be x squared plus t, then fx minus fy is x squared minus y squared, which is x minus y times x plus y. And for any polynomial in this set, it will have a similar property. For these polynomials that have this property, we can prove Solo's conjecture. And in fact, any quadratic polynomial has this property, even over the integers, which is precisely how the quadratic case was solved. But we do know also that for polynomials with rational coefficients of degree greater than 2, this never happens. So this is exactly the kind of leeway that function fields give us. And I think that's all I want to say. Thank you very much.
Thank you. Let's see. So thank you for the great talk. And now we are going to Alan Lu. Do I say it correctly? Alan Lu? Or Liu?
Leo.
Leo, sorry. Alan Leo. Alan is coming from the Technion, right?
Mm-hmm. Yes.
You wrote it. Perfect. Okay, you can start whenever you're ready.
Okay, thank you. Okay, I will talk about representability and boxicity of simplicial complexes. So first, let's talk about boxicity of graphs. In order to do that, we will need the notion of an interval graph. So an interval graph is the intersection graph of a family of intervals in the real line. For example, if we have this family of 5 intervals, we can define the intersection graph as follows. First, we assign a vertex to each of the intervals, and then we connect between 2 vertices if and only if the corresponding intervals intersect. For example, here we obtain this interval graph. Now, given any graph G, we can ask how close is G to being an interval graph. And one way of measuring this is by looking at the boxicity of G. So the boxicity of G is the minimal case such that G can be written as the intersection of K interval graphs. For example, if we look at this graph here, a cycle of length 4, then it's not hard to check that it's not an interval graph, but we can write it as the intersection of these 2 graphs, where by intersection I mean that the edges of the graph are exactly the edges that appear in both of these graphs, both here and here. But each one of these graphs is an interval graph by itself. Therefore, in this case, the boxicity is 2. Okay, this notion of boxicity was introduced by Roberts in '69, and one of the first results that he proved about it is the following result, which was also later rediscovered by Witzenhausen. And it says that any graph with n vertices has boxicity at most n over 2. And moreover, the only graph achieving boxicity exactly n over 2 is the complete n over 2 partite graph with size of size 2. For example, this graph here is the only graph with 6 vertices and boxicity 3. Okay, now we want to extend this notion of boxicity from to higher dimensions, from graphs to simplicial complexes. And we will do that through the notion of representability. Okay, so we have F, a family of sets, F1 up to Fn. We define the nerve of the family to be the following simplicial complex, n of F. The vertices of the complex are the numbers from 1 to n. So each vertex corresponds to one of the sets in the family. And the simplices are the subsets that correspond to subfamilies with non-empty intersection. For example, if F is this family of 4 sets, then we construct the nerve as follows. First, we assign a vertex to each set, and then we fill in the simplices that correspond to non-empty intersections. For example, here we have the red, black, and green triangle because the red, black, and green sets have a point in common. And okay, we define a D-representable complex to be the nerve of a family of convex sets in RD. For example, this complex here is two representable. And one important property of D-representable complexes that we will use is the following. Any D-representable complex has trivial homology in dimensions D and higher. For example, this complex here is two representable, so we know that it cannot have two-dimensional homology or three-dimensional homology or so on. Okay, now we can define what is the boxicity of a simplicial complex. So we take X a simplicial complex and some integer D, and we define the D boxicity of X to be the minimal case such that X can be written as the intersection of K D representable complexes. Okay, so first of all, this is really an extension of the notion of boxicity of graphs. In fact, for any graph G, the boxicity of G is equal to the one boxicity of the clique complex of G, where the clique complex is some simplicial complex associated with the graph. Okay, so boxicity of graphs is equivalent, essentially the same as one boxicity of complexes. Okay, and let's see an example of something new. What happens, for example, for D equals 2? We may look at this complex here, this diamond-shaped triangulation of a sphere. So this is a sphere, therefore the complex has two-dimensional homology. So we know that it cannot be two representable, but we can write X as the intersection of two representable complexes. The nerve of this family here, intersection with the nerve of this family of sets here. Therefore, the two boxicity of X is exactly 2. Okay, we are almost ready to state our main result, but we need one last definition before that. Again, X is a simplicial complex. A missing face of X is a simplex tau that does not belong to X, but any face of tau belongs to X. And we define h of X to be the maximal dimension of a missing face. For example, if X is this small complex here, then it contains two missing faces. The first one is this edge here, and the second one is this triangle here. Okay, so the triangle is not a simplex of X, but all of its faces, these three edges, for example, belong to X. So it is a missing face. So in this case, h of X is 2 because that's the dimension of the triangle, the largest missing face. And one important result related to missing faces is the well-known Helis Theorem that says that if X is D-representable, then all the missing faces of X are of dimension at most D. And it's easy to deduce from this that, in fact, if X has finite D-boxicity, then the same condition holds. The h of X is bounded by D. So if we want to talk about the D-boxicity of a complex, then it makes sense only for complexes satisfying this condition, that with missing faces of dimension bounded by D. Okay, now we can state our main result. Let X be a simplicial complex with n vertices and missing faces of dimension at most D. Thank you. Then the D-boxicity of X is bounded by this number, n choose D over D plus 1. And again, here we can characterize the equality case. The D-boxicity is exactly this number if and only if the missing faces of X form a Steiner D+1 n system, meaning a Steiner system is a family of subsets of n of size D+1 such that any D vertices that you choose are contained in exactly one set in the family. For example, here we have drawings of Steiner triple systems for D equals 2. So there are families of triples such that any two vertices are contained in exactly one triple in the family. Okay, just some remarks. For D equals 1, we recover Robert's theorem about the boxicity of graphs. And for D greater or equal than 2, this theorem improves some previous results due to Witzenhausen. Okay, so that's it. Thank you for listening.
Thank you very much. Okay. Where is my, So now we are moving to the next talk by Raz Slutsky.
Yes.
From the Weizmann Institute for Science. So, okay, you can start.
So hi, I'm Raz. I'm very glad to be here. I'm going to talk about the minimal size of generating sets of lattices in Lie groups. So this is based on a joint paper with Zorik Gelander, which was recently published. And I'd like to start with an easy example, which is both pretty cool when you look at it this way, and also captures really the essence of this line of research. So consider a surface S of genus G, which is at least 2. Then we can put a hyperbolic metric on it, which means it has constant curvature -1. And now we can use the Gauss-Bonnet theorem, which tells us the following thing: the integral over the curvature K is equal to 2 pi times the Euler characteristic of the surface, or 2 minus twice the genus. But we remember that the curvature is constant -1, so this is just the integral over -1, which is just minus the volume of the surface. And in other words, the volume of the surface S determines its topology completely. Since in dimension 2, we have classification of surfaces, and so the genus tells us everything topologically, which is quite remarkable, I think. And now I want to put this example in a more algebraic context. So denote the fundamental group of S by gamma. Then gamma is what's called a lattice in SL2R, the group of isometries of the hyperbolic plane. So a lattice is a discrete subgroup of some topological group, such that the quotient has a finite covolume. And this is the case here because S is isometric to H2, the hyperbolic plane, a quotient by gamma, which, as some of you know, is isometric to SL2R mod SO2 mod gamma. So gamma here has a finite covolume because S is a compact surface. And S is a basic example of a locally symmetric space. So these are this is a wide family of manifolds, which includes, for example, all hyperbolic manifolds of every dimension. And what's very nice about them is that we have this duality between geometry. They have a definition of purely geometric sense, dealing with the isometries and the curvature of these manifolds, to groups and algebra they all come from these semi-simple Lie groups, such as SL2R, and their fundamental group are these discrete subgroups or lattices in these semi-simple Lie groups. So this allows us to use many tools from algebra, from Lie groups, algebraic geometry, number theory, and so on. So going back to our example in dimension 2, a very surprising thing is that this phenomenon continues to hold in higher dimensions. So one of the first results in this direction is due to Gromov, and it states the following. This is from 82, I think. If X is a symmetric space, for example, a hyperbolic n space, and here I think about it as some fixed universal cover of some manifold, then there is a constant C which depends only on X, such that the sum of the Betti numbers of M is bounded by the volume of M. For every M, a finite volume quotient of X, and Bi is the ith Betti number. So here again, we have some bound on the topological complexity of our manifold. In this case, the Betti numbers, and they are all bounded by the volume of M. Now I want to move on to the rank of a lattice. So I denote by d gamma to be the minimal size of a generating set of the group gamma. Or in other words, the minimal number of elements that I need in order to generate gamma. So a recent result by Gelando says the following. I'm going back to the more algebraic setting. If G is a semi-simple Lie group with no compact factors, then there exists a constant C such that the minimal number of generators of gamma is bounded by the co-volume of gamma in G for every lattice gamma in G. So in the more geometric sense, it means that every locally symmetric space, the fundamental group of this manifold is generated by at most C times the volume of this manifold number of elements. And here is a nice implication. If we look at this inequality from the other side, we have that the volume of G mod gamma is bounded from below by this 2 over this constant C, which means that locally symmetric spaces cannot have arbitrarily small volume once we fix a volume form in G, which is also known as the Cauchy-Dalmor-Bourles theorem. So our paper deals with lattices in general Lie groups. So here we consider not necessarily semi-simple groups, or maybe they have compact factors. And I'm not going to state exactly the main theorem because it needs some modifications that would take too long due to the following counterexample. Take gamma 1, some lattice in SL2R, and now take alpha z inside R. So this is some non-semi-simple group. And the covolume of this lattice is the covolume of gamma 1 times the covolume of alpha z inside R, which is the quotient of R mod alpha z is some circle of length alpha. And so if I decrease alpha to be very small, the number of generators of this lattice stays fixed, but the covolume gets as small as I want. So what I will mention is one of the key steps in our proof, which is the generalization of result by Mostov from 1962. So Mostov studied solvable Lie groups, and they showed that the number of generators of lattices in solvable Lie groups is bounded uniformly. So our theorem is a generalization of that to amenable Lie groups. So if G is a connected amenable Lie group, then there exists a constant C such that the number of generators of gamma is bounded by C for every lattice gamma in G. So this uses some text from Lie group theory, some algebraic geometry, and is the main step in our proof. If you want to see the full statement of the main theorem, please check out the paper or contact me at this email. Thank you.
Thank you very, very much. Okay. I think this concludes this session of the Lightning Talks. I'm really, really excited and really enjoyed all the talks. I mean, they're amazing, and I'm happy that we did it. And I hope that maybe in the next year, or maybe after the German-Israeli meeting, there will be something like this, because, I mean, there are such amazing students, and they deserve to have an audience to actually give talks. But we'll see, we'll see. Anyway, thank you, everyone, and I see you next time in either Zoom or Jerusalem, right, Alex? Am I right?
And thank you, Leo, for handling all this. It was really great. Thank you very much, and the whole committee.
And thank you for all the speakers. I mean, really great. Okay.
רז, שאלה מתמטית אליך. המשפט של צחיק לחבורות סמי-סימפל, פשוטות, הוא הטוב ביותר האפשרי, או יכול להיות שאפשר לצפות לחסמים אולי אפילו יותר טובים מאשר ליניארי בווליום?
כן, אנחנו חושבים שלפחות בהיירנק זה אמור להיות סאב-ליניאר.
זה אמור להיות סאב-ליניאר, כן. אבל אין שום תוצאה בכיוון הזה.
לא שידוע.
יש לי הרגשה שייתכן לסריגים לא יוניפורמיים, יש אולי סיכוי להוכיח משהו שהוא סאב-ליניאר. באופן הבא, יש עבודות של בן קטרמנה, והסטודנט שלו, ששכחתי את שמו, שמראים שאם אתה לוקח בעצם סריג כזה, עם בעיית חברות הקונגרנציה, ל-SL3Z אני יכול לתת לך הוכחה מלאה. ל-SL3Z אני טוען שכמות, אם אתה לוקח חברות מאינדקס סופי, אז מספר יוצרים גדל לוגריתם.